I am Anuradha Rajesh. Today we shall begin the third session of chapter Light, Reflection and Refraction. Dear students, after today's session you will be able to investigate the path of a ray of light through a glass slab, calculate the value of refractive index for a given pair of media, differentiate between a convex lens and a concave lens. Define some basic terms relating to spherical lenses. Draw ray diagrams for image formation using convex lens. And discuss the characteristics of the image formed. In our previous session, we had learnt about the sign conventions used for spherical mirrors and lenses. We had always learnt about the phenomenon of refraction and the laws governing it. Today, we shall discuss the path of a ray of light through a glass slab. The given figure shows the path of a ray of light through a glass slab ABCD. Here, EO is a ray of light incident on interface AB. I hope you know that an interface is the boundary separating two transparent media. N dash is the normal to the interface at the point of incidence. It is important to draw normal as the angle of incidence will be taken as the angle between the incident ray and the normal at the point of incidence. Similarly, the angle of refraction is taken to be the angle between the normal and the refracted ray. Since the ray of light is travelling from a rarer medium, that is air, to a denser medium, that is glass, it bends towards the normal. In this case, angle I1 represents the angle of incidence and angle R1 represents the angle of refraction. As the ray of light bends and passes through the other medium, it again undergoes refraction at the glass-air interface CD. This time, the ray is travelling from a denser medium to a rarer one, that is, from glass to air. So, it bends away from the normal MM dash. The refracted ray O dash H at the second interface, that is CD, is referred to as the emergent ray, since the ray of light emerges out of the glass slab. The angle between the emergent ray and the normal MM dash is called the angle of emergence and is represented by angle R2. The extent of bending of the ray of light at the opposite parallel faces AB, that represents the air glass interface, and CD, which represents the glass air interface of the rectangular glass slab, is equal and opposite. This is why the angle of incidence is equal to the angle of emergence. Also, the ray emerges parallel to the incident ray. However, the light ray is shifted or displaced sidewards. Therefore, we conclude that when a light ray passes through a glass slab, the angle of incidence is equal to the angle of emergence. Also, the incident ray is parallel to the emergent ray, but is displaced sidewards. We are already familiar that the extent of bending of light during refraction is different for different pairs of media. For instance, bending of light at air-glass interface will be different from the bending of light at air-kerosene interface. The extent of the change in the direction that takes place in a given pair of media may be expressed in terms of refractive index. The refractive index can be linked to an important physical quantity, the relative speed of propagation of light in different media. It turns out that light propagates with different speeds in different media. Light travels fastest in vacuum with a speed of 3 into 10 to the power 8 meters per second in air. In air, the speed of light is only marginally less compared to that in vacuum. It reduces considerably in glass or water. The value of refractive index for a given pair of media depends upon the speed of light in the two media. Let us consider a ray of light travelling from medium 1 into medium 2 as shown in figure. Let V1 be the speed of light in medium 1 and V2 be the speed of light in medium 2. The refractive index of medium 2 with respect to medium 1 is given by the ratio of the speed of light in medium 1 and the speed of light in medium 2. This is usually represented by the symbol N21. This can be expressed in the equation form as N21 equal to speed of light in medium 1 upon speed of light in medium 2 equal to V1 upon V2. In a similar manner, the refractive index of medium 1 with respect to medium 2 is represented as N12 and is given by N12 equal to speed of light in medium 2 upon speed of light in medium 1 equal to V2 upon V1. Since we in general study the refraction occurring from air to other media, so we may fix the first medium to be air or vacuum, where the speed of light is almost the same as air. Then the refractive index of medium 2 is considered with respect to air or vacuum. This is called the absolute refractive index of the medium, or simply the refractive index of a medium. If c is the speed of light in air or vacuum and v is the speed of light in the medium, then the refractive index of the medium is given by Nm equal to speed of light in air upon speed of light in the medium equal to c upon v. Since refractive index is a ratio of speed of light in two given media, it does not have any unit. The absolute refractive index of some material media is given in the table shown. A higher refractive index indicates a higher optical density or lesser speed of light in the given medium. Here, diamond has maximum refractive index of 2.42. So, it has the highest optical density or least speed of light among the given media. It is to be noted that optical density is the ability of a medium to refract light. An optically denser medium may not possess greater mass density. For example, kerosene has a higher refractive index than water, although its mass density is less than water. Let us solve a numerical based on refractive index. Light enters from air to glass having refractive index 1.50. What is the speed of light in the glass? Given the speed of light in vacuum is 3 into 10 to the power 8 meter per second. Here, the refraction occurs from air to glass. Therefore, we may consider the absolute refractive index of glass to be 1.50. Refractive index of glass is given by speed of light in vacuum upon speed of light in glass. Substituting the values of speed of light in vacuum, we will have Ng equal to C by V, that is 1.5 equal to 3 into 10 to the power 8 upon V. Using mathematical calculations, we can find the value of V to be equal to 2 into 10 to the power 8 meter per second. One numerical has been done with you all. Do practice more numericals from your textbook. So students, you might have seen watchmakers using a small magnifying glass to see tiny parts. Have you ever touched the surface of a magnifying glass with your hand? Is it a plain surface or curved? Is it thicker in the middle or at the edges? do check out. The glasses used in spectacles and that by a watchmaker are examples of lenses. What is a lens? A transparent material bound by two surfaces of which one or both surfaces are spherical forms a lens. This means that a lens is bound by at least one spherical surface. In such lenses, the other surface would be plane. A lens may have two spherical surfaces bulging outwards. Such a lens is called a double convex lens or simply a convex lens. It is thicker at the middle as compared to the edges. Convex lens converges light rays as shown in figure A. Hence, convex lenses are also called converging lenses. Similarly, a double concave lens is bounded by two spherical surfaces curved inwards. It is thicker at the edges than at the middle. Such lenses diverge light rays as shown in figure B. So, they are called diverging lenses. A double concave lens is simply referred to as concave lens. A lens, either a convex lens or a concave lens, has two spherical surfaces. Each of these surfaces forms a part of a sphere. The centers of these spheres are called center of curvature of the lens. The center of curvature of a lens is usually represented by letter C. Since there are two center of curvatures, we may represent them as C1 and C2. An imaginary straight line passing through the two centers of curvature of a lens is called its principal axis. The central point of a lens is its optical center. The effective diameter of the circular outline of a spherical lens is called its aperture. If we carefully observe figure A, several rays of light parallel to the principal axis are falling on the convex lens. These rays, after refraction from the lens, are converging to a point on the principal axis. This point on the principal axis is called the principal focus of the lens. In figure B, however, several rays of light parallel to the principal axis are falling on a concave lens. These rays, after refraction from the lens, are appearing to diverge from a point on the principal axis. This point on the principal axis is called the principal focus of the concave lens. If you pass rays parallel to the principal axis from the opposite surface of the lens, you will get another principal focus on the opposite side. Capital letter F is usually used to represent principal focus. Since a lens has two spherical surfaces, it has two principal focus. They are represented by F1 and F2. The distance of the principal focus from the optical center of a lens is called its focal length. Small letter f is used to represent the focal length. In our previous session, we had learnt about image formation using mirrors. We use certain special rays for drawing ray diagrams. Similarly, in case of lenses also, there are certain special rays which we shall use to frame images. An image is formed when two or more light rays after refraction through the lens either meet or appear to meet. When there is an actual intersection of light rays after refraction, a real image is formed, whereas a virtual image is formed due to the apparent intersection of refracted light rays. Let us now discuss the special rays used for making ray diagrams. A ray of light from the object parallel to the principal axis after refraction from a convex lens passes through the principal focus on the other side of the lens as shown in the figure. In case of a concave lens, the rays appear to diverge from the principal focus located on the same side of the lens. A ray of light passing through a principal focus after refraction from a convex lens will emerge parallel to the principal axis. This is shown in first figure. A ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis as shown in the second figure. A ray of light passing through the optical center of a lens will emerge without any deviation. So, let us now start image formation using convex lens. But before that, I have a small but important tip for you. Whenever you are making a ray diagram, you should make sure that the distance of either foci from the optical center is the same. Also, the points 2F1 and 2F2 are marked at twice the distance between the optical center and the focus of the lens. If they are not marked correctly, you may not be able to make correct ray diagrams even if you use the correct set of rays. So now, let us consider the case when the object is placed at infinity. The light rays from infinity is represented by a set of parallel rays. If we consider them to be parallel to the principal axis as well, they would meet at focus, forming a real, inverted and a highly diminished or point-sized image. For an object AB held beyond 2F1, perpendicular to the principal axis, we may consider two rays starting from point A. The ray which is parallel to the principal axis after refraction shall pass through the focus on the other side of the lens. On the other hand, a ray passing through the optical center will pass through the lens without any deviation. The two refracted rays will meet between F1 and 2F1, forming a real, inverted and diminished image. When the object AB is placed at position 2F1, the image is formed by considering two rays starting from the tip of the object, that is point A. One ray here is taken to be parallel to principal axis. After refraction through the lens, it passes through the focus on the other side of the lens, and the other ray is taken to be the one passing through the optical center. This ray does not suffer any deviation. The two refracted rays actually meet at 2F2, forming a real, inverted and same sized image. Now moving on to our next case, wherein the object AB is placed perpendicular to the principal axis anywhere between F1 and 2F1. The image is formed again by taking the same set of incident rays as in the previous case. The image thus formed is real, inverted and enlarged. Now, we shall consider the object at the focus F1 of the lens. A ray starting from the tip of the object parallel to the principal axis after refraction shall pass through the focus on the other side of the lens. The other ray has been taken to be the one passing through the optical center. This does not undergo any deviation after refraction through the lens. It is interesting to note that the pair of refracted rays turn out to be parallel to each other. Such rays will form an image at infinity. The nature of image will be real and inverted, while the image will be highly enlarged with respect to the object. Let us now move forth to the last case for convex lens, wherein the object is placed between the optical center O and focus F1 of the lens. Here we consider the first ray starting from the object to be the one parallel to the principal axis, which passes through the focus F2 on the other side of the lens. The other ray is taken to be the one passing through the optical center of the lens. We observe that the two refracted rays form a pair of divergent rays which do not actually meet. However, a point of apparent intersection can be found by extending the two refracted rays backwards. An image A', B' is thus formed at the same side of the lens as the object. Since the image is formed due to apparent intersection of light rays, it will be a virtual and erect image. The image is enlarged with respect to the object. Dear students, now we will experimentally observe certain cases of image formation using a convex lens. First, let me explain the experimental setup. The setup consists of a pair of meter scales. Over the scales, uprights have been mounted in order to hold the lens and the screen. A candle flame shall act as the object in our case. Let me light up the candle. In the first case, we shall place the lens at a distance more than 2f from the object. The lens which we are having is a convex lens of focal length 20 cm. So, we shall place the flame at a distance more than 40 cm from the object. Here we are. We can observe an image to be formed between f and 2f of the lens. That means between 20 centimeters and 40 centimeters from the lens. Let us have a look at the image formed. You can clearly see that the image is real, inverted and diminished with respect to the object. Now let us try to observe the image when the object is placed between f and 2f of the lens. That means between 20 and 40 centimeter from the lens. Let us try to frame an image. I am bringing the lens nearer to the object and placing it at a distance between 20 and 40 centimeters from the object. Now, let me try and focus the image onto the screen. Here we are. The image which is formed is clearly formed at a distance beyond 40 centimeters, that means beyond 2f from the lens. The image thus formed is real, inverted and enlarged with respect to the object. Do keep practicing. Meet you in the next session. Thank you.